So in this part, we're going to see how the relative abundance part works of the mass spectrometer. So like I said, that you would have one peak that is the relative abundance, and then you would have the mass by charge in the other axis, in the x-axis. So let's imagine that you have a bromine molecule. Okay, so so you have Br2. So you are injecting that sample, right? So there are basically four ways in which a bromine molecule could form. So we already know that bromine has two isotopes. One is 79 bromine, the other one is 81 bromine, right? So these Br2, they can be formed from 279 Brs. They can be formed from 179 Br, and the other one could be 81 Br. Or you could also have the first one as 81 Br and the next one as 79 Br. So these are the three ways you can form it. And the last one is you can have both 81 Br isotopes. So in this case, well, we already know that the abundance of 79 Br is 50%, and the abundance of 81 Br is also 50%, which basically means that if you take a sample of bromine anywhere in the world, anywhere, so in that sample, you're gonna have 50% 79 Br and 50% 81 Br. So what we do here is, so if we inject this Br2 molecule sample into a mass spectrometer, so inside the mass spectrometer it is ionized first. So a 79 Br could be ionized. So that way I will have 158 m by E, right? If the charge is +1. And for these guys, I can have 71 and 81 plus, or 81 and 71 plus. Notice that we have to have pluses, because if it is not positive, it won't be accelerated or deflected in the mass spectrometer. So 81 and 79, they both are going to give m by E of 160. Excuse me. And an 81 and 81 is going to give an m by E of 162. So let me highlight them. So this is the 158, 160, and 162. So I know that inside the mass spectrometer, I'm going to see at least 3 peaks for the Br2 molecule in a mass spectrometer. But what about their heights? So I know that they are each 50%. The probability is half, right? So we can calculate this. So for this guy, 79, 79, what you need is you need a 79 bromine and another 79 bromine. And in probability, we know that whenever we have and, we multiply the probabilities. So the probability of this guy is the probability of 79 bromine and another 79 bromine, which is half. So the probability, this guy's probability is 1 by 4. So if we look at this one, 81, 81, we know that the probability of 81 Br is also half. So you need 181 half, 181 Br, and another 81 Br to produce 162. So we multiply it again. So we get 1 by 4, 1 by 4. So the abundance of 158 peak and the abundance of 162 peak are going to be the same. But let's look at this one. This is interesting. So in here, what we have is, let me elaborate them. Let me write them somewhere else, okay? So this is the 79 Br. It is bonded to an 81 Br. Or you can have an 81 Br that is bonded to a 79 Br. So in this case, to produce this, I need half times half, because the probability of having a 79 Br is half, and that needs to be with an 81 Br, which is also half. And whenever we have or in probability, this is a plus. This is half, again, and this is half. So if we add them up, so we have 1 over 4 plus 1 over 4. So 1 over 4 plus 1 over 4, this gives us 1 half. So we know this as well. So we know their abundances, right? This is 1/4, this is 1/4, and the middle one is 1 half. So if we draw the mass spectrometer curve, the plot, so this is relative abundance, and this is the m by e. So I'm gonna have one peak at 150. I'm gonna have one peak at 158. So let's say this is 158. I'm gonna have one peak at 160. I'm gonna have one peak at 162. So the height of 158 is 1 by 4. The height of 162 is also 1 by 4. So 158 and 162 are gonna be 1 by 4, the same height, right? So that's they're the same height. But now let's look at this one, the 161, which is this one. Its height is 1 half. So its height is twice that. 1 half is twice of 1 by 4. So this is how you would see it. And also don't forget that fragmentation could occur. These bonds can break in half. And if that happens, you would also see some peaks at 79 and 81. So these are the fragments, right? These are from fragments of bromine molecules splitting up. So likewise, for chlorine, we have two isotopes, right? One is 35 chlorine. This has an abundance of 75%, or we could call it 3 by 4, and 37 chlorine. 37 is then 25%. So we call it 1 by 4. So now if we insert a chlorine sample, a Cl2 sample, inside a mass spectrometer, the ways in which a Cl2 molecule could form are 35 chlorine bonding with another 35 chlorine, 35 chlorine bonding with a 37 chlorine, or a 37 chlorine bonding with a 35 chlorine. And lastly, we can have a 37 chlorine bonding with a 37 chlorine. So if this becomes ionized, so just like the bromine case. So for this, I'm going to have a 70 m by e. Here I'm going to have a 72 m by e. And here I'm going to have a 74 m by e. And their heights, so this guy's height is going to be, so the probability of a 35 is, 3 by 4, right? So this is 3 by 4 times 37. So 35, these are both 35s. So I'm going to have 3 by 4 times 3 by 4. So 3 by 4 times 3 by 4, this is 9 by 16. And this guy is, like we've seen in the case of bromine, it's going to be 3 by 4 times 1 by 4 plus 1 by 4 times 3 by 4. So this is 3 by 4 times 1 by 4 plus 1 by 4 times 3 by 4. So this is going to be, so this is going to be 3 by 16 plus 3 by 16. So this is going to be 3 by 8. 3 by 8, or we could say 6 by 16. And this guy is going to be 1 by 4 times 1 by 4. So this guy's going to be 1 by 4 plus 1 by 4, which is, oh, this is multiplied. So this is going to be 1 by 4 times 1 by 4, which is 1 by 16. So these are the heights that we're going to see. 9 by 16, 6 by 16, 1 by 16, right? So if we multiply all of them by 16, then the height ratios are going to be 9 is to 6 is to 1. So if we have a plot, if we have a mass spectrometer plot for these guys, so this is M by E, this is the relative abundance, so this is the relative abundance. So I'm going to see a peak at 70, 72, and 74. So let's draw the peaks. So let's call this one 74. Let's call this one 72. Now let's call this one 70. So the height of the 70 is going to be 9. So this is going to be 9. The height of 72 is going to be 6. So that's probably around here. And the height of this is going to be 1, so we need to make it smaller. So 1 is probably here. Okay. And also now, don't forget that we can also have fragments at 35 and 37, right? So there'll be a fragment at 3 by 4, which is it's supposed to be smaller than 1. Okay, it's going to be smaller than this guy. So we're going to have one at 35. We're going to have one at 37. So notice that the relative atomic mass of one chlorine is 35.5, but that's the average, right? We'll never see an average mass in the mass spectrometer because we see the mass of each individual isotopes. So we're going to see the peak of 35 and 37. So 35 has a more abundance than 37, so it's going to be a little bit taller than 37. So we're going to see that. So the way we figure 35.5 out is, so we have 35, which is 75%, and then we have the 37 isotope at 25%, and divided by the total is 75 plus 25. So this is not always 100. So you have to realize this, it's not always 100. So if we calculate that and we multiply it by 100, so then we'd see that, no, we don't, so what we would see here is the average is 35.5. So let's double check. 35 times 75 plus 37 times 25 divided by 100. So, we don't need to do this. Don't worry about this. So, yeah, so that's the relative atomic mass of one chlorine. So this is because it's hard to deal with each isotope individually. So what we do is we take the abundance of each isotopes of a particular element and we just average them out, right? So we work with the average. So that's that. So like I've said, that always be careful when calculating the relative atomic mass. So in here, this is a question paper from Pearson at Excel. So here you're given mass spectrometer data. So you have M by E on here, you have M by E in the x-axis, and then you have the relative abundance in the y-axis. So these are the options. So if we see the way we're going to calculate this is, so the height of the 63 is 1, 2, 3, 4, 5, 6, 7. So the height here is 7. It's 7 units up. We don't know what those units are. We don't care. And this one is 1, 2, 3. So this is one is 3 units up compared to this guy. So the way we would calculate the relative atomic mass is of this compound is going to be 63 times 7 plus 65 times 3 divided by 7 plus 3. So remember here we did 75 plus 25. So it's not always 100%. Like look here, it's not 100. It's not 100. It's 10. So this is going to be 63.6. So our answer in this case would be B.